Hello everyone, Integrals 1, day number 6. Topic for today are advanced integration of trig functions, where we'll be using trig identities pretty heavily. And the second part will be integration resulting in inverse trig functions. And in that part we're going to employ some shortcuts. It'll be nice. Alright, let's get started. Okay, let's get going on advanced trig integrals. So the method that we're going to use is using trig identities to isolate a single trig function. Typically we want to isolate either a sine or a cosine so that we can use substitution to simplify the process. So in number 1 I see sine cubed x. You can play with that as much as you'd like, however you're not going to likely in that form find a way to integrate. So I am going to rewrite, instead of sine cubed, I'm going to write it as sine squared x times sine x. And then I'm going to substitute in for sine squared x 1 minus cosine squared x. So this becomes the integral of 1 minus cosine squared x times sine x dx. So that second sine x comes right there, and I use an identity for the rest. Okay, so then what I'm going to do is distribute. So I'll have the integral, distribute a sine x to both terms. I'll have sine x minus sine x cosine x. So when I say isolate a single function, I am isolating a single sine x at the end, such that when I use a u substitution, the derivative of cosine will be related to that sine value. All right, so, oops, I want to go in a different color. Here we go. All right, so I'm going to rewrite this as two integrals. The integral of sine x with respect to x minus the integral of sine x, and that should be a cosine squared x dx. Now, anytime you see two trig functions, specifically sine and cosine, multiplied together, whichever one has the larger power likely will end up being your function used for u, or used as u. So I'm going to set u equal to cosine x. Therefore, du equals negative sine x dx. And therefore, I'd have negative du equal to sine x dx. All right, so what we'll have here is the integral of sine, which is negative cosine. And then, let's see here, we can replace sine x dx with negative du. Actually, you know what, I shouldn't have done that. Let's leave that as a negative sine x. Then we can replace all of that. So that would be plus the integral of cosine squared, which will be u squared, times du, which will come out to be negative cosine of x, plus, that would be u cubed over 3, but I'm going to just write it as cosine cubed x over 3 plus c. And there you have it. That's the integral of sine cubed dx. All right, let's look at number 2. Number 2 is relatively complex, and it looks like both sine and cosine have the same power, so I'm going to choose to break down cosine x, and I typically do that because the derivative of sine is cosine, whereas the derivative of cosine is negative sine, so it can kind of, all those negatives involved can be, well, annoying. So I'm going to write this as the integral of sine to the 5th x, and I'm going to break cosine to the 5th into cosine squared, cosine squared, cosine. And cosine squared is 1 minus sine squared x. So there's cosine squared, and another cosine squared, left with one cosine isolated at the very end. Okay, so let's do a little foiling. This will be the integral sine to the 5th x. If I FOIL these two binomials together, I'd get 1 minus 2 sine squared x plus sine to the 4th x cosine x dx. I'm going to distribute sine to the 5th to each of those three terms within the parentheses. That'll be sine to the 5th x minus 2 sine to the 7th x. You might see it coming here. plus sine to the 9th x. Well, what would u equal in this situation? You should answer that to yourself. U will equal sine x. We kind of discussed that at the beginning, so there's a little hint there. Derivative of sine x is cosine x dx. So I'm going to replace every sine value with u. So that's u to the 5th minus 2u to the 7th plus u to the 9th. And then cosine x dx replaces with du. Therefore, our integral will be u to the 6th over 6, which is sine to the 6th over 6, minus 2u to the 8th over 8. That'll be 2 sine to the 8th over 8. We could reduce that to 1/4 if we wanted, plus sine to the 10th over 10 plus c. There's your integral of sine to the 5th x cosine to the 5th x dx. All right, number 3 here looks pretty simple. It's not as easy as it looks. You need a special process, and in this case it's not that complex, but it's just not often used and it's not often seen. We need what's called the power reducing formula in order to integrate cosine squared x dx. So 2 cosine squared x minus 1, we know what that is. That's cosine of 2x. It would be a lot easier to integrate cosine 2x than cosine squared x. So I'm going to add 1 divided by 2, and I'll have a replaceable power reduced formula. That'll be 1 plus cosine 2x over 2. We can integrate that much easier. Let's do it. So I'm going to rewrite this. I'm going to pull out a half and rewrite cosine squared as 1/2 times 1 plus cosine of 2x dx. Very useful. Also useful when integrating sine squared dx. So 1 minus 2 sine squared x is also equal to cosine 2x. Can be reduced in the same way, so, or a similar way. Sine squared x would be 1 minus cosine 2x over 2. There you have it. Okay, let's finish up our integral here. We're going to integrate 1 with respect to x, which would be x, and we're going to integrate cosine 2x with respect to x, which would be 1/2 sine 2x. Right? I used a little chain rule. Excuse me, not chain rule. U sub in that situation. So I'm going to distribute 1/2 and get x over 2 plus 1/4 sine of 2x plus c. Don't forget c. There you have it, integral of cosine squared x dx. Maybe be able to do the integral of sine squared. Who knows? All right, let's move on and talk about inverse trig shortcuts. Okay, so let's start with number 3. Number 3 should be a breeze. The integral of 1 over x squared plus 1. That should be known to you as the arctangent of x plus c. So how would we integrate 1 over x squared plus a squared? Let's assume a is a real number. Okay, so this is interesting. What I can do, though, is I can factor out an a squared. And I'm going to use a u substitution here in a minute. But if I factor out an a squared, I would have 1 over x over a quantity squared. And if I factored a squared out of x squared, I'd have x squared over a squared plus 1 dx. Now, that's almost in a form where I can use a u sub. Well, it is in a form I can use a u sub, and I'm going to, right? So what if u equaled x over a? Well, du would equal 1 over a dx. So let's rewrite this and work through it slowly. So let's say I had 1 over a times 1 over a times the integral of 1 over x over a squared plus 1. Well, I could replace one of those 1 over a's with and dx with du. So let's go back here, and we're going to replace one of these 1 over a's and the dx with du. And we're going to replace x over a with u. So let's see what it looks like. That'd be 1 over a integral of 1 over u squared plus 1 du. So the integral of 1 over u squared plus 1 would be arctangent of u plus c, which would be 1 over a arctangent of x over a plus c. All right, so you're telling me, yes I am, the integral of 1 over x squared plus a squared dx is equal to that. Yes, every time. So if we can identify a, we can integrate anything that comes in this form. So let's look at number 5. I'm going to factor out the numerator. I always do. All right, and I'm going to rewrite the remaining portion in a form that resembles 1 over x squared plus a squared. So that'd be x squared plus 4 squared dx. So in this case, a equals 4. So this would be 5 times 1 over a arctangent of x over a, which is 4, plus c. So our integral of 5 over x squared plus 16 is 5/4 arctangent x over 4 plus c. Pretty simple example. Let's look at one that has a little bit more to it. Okay, number 6. Again, I'm going to factor out the 5. And I want this in the form x squared plus a squared, so I'm also going to factor out a 9. So this will be 1 over x squared plus 64/9 dx. So let's put this in the form x squared plus a squared. So it's 5 over 9 integral 1 over x squared plus something squared dx, which would be 8/3. Okay, so in this case, a equals 8/3. So what would 1 over a equal? Well, it would be 3/8, right? Reciprocal. So the integral of 1 over x squared plus 8/3 squared is going to be 3/8, which is 1 over a, arctangent of x over a, or 1 over a times x, which would be 3x over 8 plus c. We'll clean this up just a little bit. That would be 5 over 24 arctangent. Wow, I tried to write a 3 and it didn't look like a 3. 3x over 8 plus c. There you go. Some advanced shortcuts to integrals involving inverse tangent of x. Let's look at arc sine of x. Okay, in a very similar way, and I'm not going to go through the intricacies of number 8. You can do that on your own and ask questions if you got them, but we know that the integral of 1 over the square root of 1 minus x squared dx is arc sine x plus c. You should be nodding your head even if you didn't know that. Okay, so the integral of 1 over the square root of a squared minus x squared, very close to arctangent's same form, except it's not going to have a 1 over a on the outside. It's just going to be nice and simple, arc sine of x over a plus c. You can do the same process that I did, or very similar at least, on the previous page for that like quasi-proof. Okay, so let's get number 9 in a form where I've got 1 over the square root of a squared minus x squared. So I'm going to factor out a 4 because I want to have 1 over this thing. And I'll put 10 squared minus x squared dx. Therefore, a equals 10. So it's going to be nice. It's just going to be 4 arc sine x over a plus c. That's our integral. Real nice. Let's look at number 10. A little bit more complex. Got a little bit more to it. All right, let's do it. So let's pull out a 3. But I want a squared minus x squared. So I'm also going to, and I'm not going to do it all quite yet, but I'm going to take a 4 out of both of those terms. That would leave 7, that would leave me with 7 over 4, 7/4 minus x squared. Now if I pull that 4 out, when it comes out of the radical, it becomes a 2. Right? Square root of 4 is 2. So then I'm left with something squared minus x squared. Well, that's going to be the square root of 7 over 2. So a is equal to the square root of 7 over 2. Okay, so let's write this out. Again, we don't need 1 over a outside of the arc sine. So we're just going to have 3/2 arc sine of x over a. So x over root 7 over 2 is the same as 2x over root 7 plus c. All right, there you have it. I'm going to go over on the next slide an interesting application of this whole process, also involving completing the square. So let's do it. Okay, so a bit of a challenger, like I mentioned. Completing the square, we're going to revisit it. Prior to this, completing the square was, we had to have the denominator in some form, some binomial squared plus 1. Now we don't need that, right? Now we can have x squared or something squared plus any number, a squared. So let's rewrite what the integral of 1 over x squared plus a squared equals. It's going to be 1 over a arctangent of x over a plus c. All right, so let's find out what a is in this case. First thing I'm going to do, I'm going to factor out 3 out of the denominator. That leaves me with 1 over, well, that 3 just went away, x squared minus 4x plus 8. Okay, cool. Well, that's not a trinomial that's able to be written as a squared binomial. So what we're going to do is take x squared minus 4x. I'm going to add something, and we're going to subtract that same something. And that something will be half of this term squared, half of the coefficient squared. So half of negative 4 is negative 2 squared, you get 4. So I really haven't changed the denominator because I've added and subtracted 4. This is all with respect to x. All right, so why do I want to write x squared minus 4x plus 4? Why did I take half of it and square it? Well, because that satisfies writing this as a squared binomial, right? Which is great. It's called completing the square for a reason. Because now what I can do is I'm going to be able to do a u substitution. And 8 minus 4 is 4. And I've got myself in a real nice situation, right? If u equals x minus 2, then du is equal to dx. We can do a clean sub here. And that's looking a whole lot like an arctangent integral. All right, so I've got 1/3. What is a? A is not 4, a is 2, right? Because 2 squared. So then 1 over a arctangent of, oh, hey now, slow down. Not x over a, u over a plus c. And what was u? U was x minus 2. So this is 1/6 arctangent, got a little crazy there, x minus 2 over 2 plus c. There is the use of completing the square as well as some advanced techniques. So hope it went well for you. Let me know if you got questions. Make sure you do your sets and reps, and we'll see you in the next video. Have a good one.